All right, welcome to week 6. Got some great news for you. Very light week this week, relatively easy stuff. In my experience, taking some time to really learn how to use some of these measurements, measuring tools, and use some of this equipment is going to be really important. Please make sure that you have picked up one of the lab kits. We are going to be using the circuits for this week in a very small lab. If you haven't picked it up yet, I'm available Tuesday evenings from 6 to 7 p.m. As well as Wednesday from 11 to 1:15 out at the Williams campus. Okay, all of that information has been in Canvas, but I will still be there with those lab kits. So this week we're going to explain current, voltage, and resistance along with how they affect one another, and then we are going to learn how to build and calculate and measure different values and circuits. Okay, I've decided to break up my circuits unit, so this week is literally just an intro to circuits and Ohm's law. Okay, and then we'll look at the difference between series and parallel and all of the rules that come with series and parallel circuits. Then we're going to combine them into combination circuits, and then from there look at some Kirchhoff's laws. So I don't exactly follow necessarily the way the textbook does this, so we're going to jump around a little bit. But after years and years of teaching circuits, and I absolutely love teaching circuits, but after years of teaching it, I truly believe that this is the best way to do it. Okay? So the first thing we need to really understand is what current, voltage, and resistance are. So potential difference we've already discussed, right? Our potential difference was that change in potential. We know that it's capital V is the symbol, and we are looking at volts or joules per coulomb as the unit. Now, when we talk about circuits, we either use a V or a delta V. That change in voltage or the potential difference is a drop between 2 points. So for instance, on this battery down here in this picture, if we were to measure the voltage drop between this point and this point, this is where we would place the probes of your multimeter in order to measure that. Okay, so that's why it's called a potential difference, because it's a difference between 2 points, and we often refer to it as a voltage drop. Okay, and although we looked at a joule per coulomb, we're more frequently going to use volts for this, which makes it nice and easy in our equation because V is measured in V's. So that should be nice and simple. Just note the potential difference means the voltage. When we talk about an analogy, because it's hard to understand what voltage really is, and so if you think about water in a tube or going through your pipes, think of voltage as that water pressure. If you don't have a water pressure difference, then that water's not going to move. All right, so same thing here in a circuit. If you don't have that potential difference, okay, which is the work per charge, if you don't have that potential difference, there's not going to be any flow of electrons. There's not going to be any current going through that circuit. Which brings us to current, okay? Current is a flow of electric charges through a conductor or a circuit. Our conventional current, sorry, I don't know what happened to my notation here. Our conventions say that we go from positive to negative. Now, if you talk with electricians or even some engineers, then they may say the opposite, which is also true, that those electrons, the way that they actually flow. However, in physics, we are going to use the convention that we have a positive side that flows to a negative side. Okay, part of your lab simulation, you're going to have you're going to toggle back and forth between the electron view versus the conventional view. But just so we know that everyone's on the same page, we use conventional current for this class. So current is dependent on the amount of voltage and the resistance. That is going to be one of your labs that you're going to look at how one affects the other, okay, or how they both affect current essentially. The symbol for current is I. I like to try to use a capital I like this. Some different fonts, it's hard to actually see if that's an I or a 1. So if you're handwriting these, please use a capital I. I try to use a font that shows that I, or I use the equation, the insert equation, the equation generator that has that capital I. Okay. The reason it's I, it comes from a French scientist, Amperes, which its unit is named after. And an ampere is a 1 coulomb per second, which we'll get to here in a sec. But an ampere is Ampere was a French scientist. And so when we had more current, we would see brighter bulbs. And so he called it the intensity, or in French, it's intensité, which is why it is a symbol of an I. The symbol C is actually capacitance, which is why current is not C. Okay, so I is going to be our current. It is measured in amps, which you can shorten into A or AMP. All right, and it is the amount of coulombs per second, which means we have a Q divided by our change in time. So how many coulombs are passing a specific point at a given time? So it is a rate of change similar to how velocity was meters per second. This is how many coulombs per second are going through there. Now we say that in reality, it's more of an energy push. Those electrons don't travel all the way around the loop like the water would flowing in a pipe. It's more of a pressure difference in terms of that energy moving through the wires. We'll talk a little bit more about that later, but just so you know. Okay, but the current is the amount of coulombs divided by time. Okay. So that is going to be in your expert TA, is focusing on using that equation as well as our next one that we'll get to here in a second. So our last piece to the puzzle here is our resistance. Now I put two different columns in here because we have resistance and then we have a resistor. So a resistance is the opposition of flow of charges. I like to call it the friction of electricity. There is an entire section, which is 9.3 in your textbook, that goes into detail about resistance and the factors that affect it. We'll look at those a little bit in later chapters or later units, but for right now, if you're interested in looking at that, you can. Those of you going on into circuits classes, you'll probably study that a little bit more in terms of resistivity and what affects that. Okay. We are going to assume a perfect world, like we always like to do in physics, where we don't have any internal resistance. In reality, we do. So when you do labs in the simulation, you're going to get really perfect numbers, whereas when you actually build these with our breadboards and our circuit kits, you might not get the same perfect numbers. So if you're measuring your, let's say, 100 ohm resistor and you're getting 98 or something like that, that's okay because we have some internal resistance. There's internal resistance in the battery, in the wires, as well as the resistors themselves. So a resistor, we've got two different things. So we can use, these are non-ohmic resistors, so things like light bulbs, hair dryers, and stuff like that. And then we have ohmic resistors, which are these devices, which you should see in your lab kits. And these devices are meant to manipulate the flow of current. All right, so when we have something like a circuit board, what each of these is doing is actually manipulating the current to make the current go up or the current go down based on what component that is attached to. For instance, in your lab where you're actually building, if you connect an LED to the board without using a resistor, that is way too much current for it. It will blow. So please do not do that, okay? Please make sure you're following directions for those labs. It is really important. All right, so the resistor will actually adjust up or down depending on how you build that circuit to make it a specific amount of current. So that's why we use resistors like this. And then we consider these a type of resistor that actually use those devices, as I mentioned, in terms of different objects that require that energy. So resistance is a capital R, and it is measured in ohms, okay, which we're going to look at Ohm's law. And for ohms, we use the Greek letter omega, which looks like a little horseshoe. We use omega instead of O because O obviously looks like a 0. So anytime you are typing up answers and you need to use the omega, you can insert a symbol and you can find that symbol. Or if you would rather just type ohms, it's not a long word, you can just type that as well. So our last relationship, I'm always hesitant on giving you because our lab simulation this week, you're actually deriving this formula. So you're going to manipulate different voltages and look at the current, and you should get a nice straight line, and you should get a equation to a line that looks very similar to Ohm's law. So Ohm's law is actually usually written in this form like this, where we have our voltage is equal to our current times resistance. I personally, however, prefer to write it in terms of current, because as you're going to see in our labs, that the current is actually dependent on both the voltage and the resistance. Okay, so whatever happens to the voltage, the same thing's going to happen to the current, and inversely with the resistance and current. So this is kind of both ways. Essentially, we're going to be using this equation many times over the next month. All right. So the good news is you don't have nearly as many equations. In fact, I think we have like 3 equations for the next couple of weeks. But we're going to use this endlessly in many different situations. I also love this little cartoon here that shows you exactly what's happening. We've got the amps, which is the flow of electrons, or it's that, theoretical flow of electrons, that energy moving through the wires. We've got the voltage, which is that pressure pushing that amperage through the circuit. And then the ohms, which is the resistance. This one's kind of showing that internal resistance of, reducing or making it hard for those amps to move through. And, but again, we can use actual resistor as well. So that's pretty much it for this week. We've got